Welcome to lesson 1.5. This lesson is all about inverses. So let's start by talking about an inverse. Basically, to begin with, an inverse is defined as taking two equations, and you could do g of f of x and f of g of x using that function composition we learned last lesson, and both of those equal x. If that is true, then we say that those two equations are inverses of each other. So in this first example, we're going to prove that. So we're going to try g of f of x and f of g of x. And both of these should equal x. If they do, then the two equations are inverses of each other. So in this first one, I'm plugging f into the g equation. So there's my g equation, 1 over x minus 2. And I'm going to plug f into that. So 1 over x plus 2. There's my f equation plugged into g. So first thing I'm going to do here is keep switch flip. Keep the numerator, switch to multiplying, and flip the denominator. So, and then I still have that minus 2 hanging out. 1 times 1 over 1, that's all going to go away. So I just have x plus 2 minus 2. And that equals x. That's what I wanted. Sweet. So let's try the other side. Now we're going to plug g into f. So here's my 1 over x plus 2. That is my f equation. And I'm going to plug g into that. So there's g plugged into f. So first thing I notice, this is minus 2 plus 2. So that's just going to go away. Then keep switch flip, keep the numerator, switch to multiplying, flip the denominator. And 1 times x over 1 equals x. Ta-da! So we did g of f and f of g. They both equaled x, so we know that these two things are inverses. Now, another way that we think about inverses is by looking at the graph. So let's look at f of x equals x squared right now. We know f of x equals x squared. That's one of our parent functions. It's the parabola. We've seen this before. Now, if you just think, what is the inverse of x squared? Meaning, like, what is the opposite of x squared? All of you would probably pretty quickly come up with square root of x. That is the opposite of x squared, the inverse. Now, however, don't forget every time you have a square root, you have a plus or a minus. So the positive square root of x would be this. That's your positive square root of x. Your negative square root of x would be this. That's the negative part of it. You could also think of it as a reflection down. And if you put that all together, you'll see that this is the graph of the inverse parabola. Basically, we take our parabola, turn it on its side, and that's the graph of the inverse. But you should pretty quickly notice that this graph is not a function. It does not pass the vertical line test. So this graph is not a function. It's a good graph, but not a function. So we want to come up with a new test so that I can look at this graph and not just find out if the graph is a function. That's the vertical line test. It tells us if the graph is a function. I want to tell if the inverse is a function. Well, that is what we call the horizontal line test. You'll notice here on my parabola, if I did a horizontal line test, it passes the graph more than once. So the horizontal line test tells you if the inverse is a function. So let's summarize all that. Vertical line test is it a function? Oops, that's a weird T. The horizontal line test is its inverse a function. And we say if it passes both of these, so if the original is a function and the inverse is a function, we call that one-to-one. So let me give you an example of that. Hopefully some of you will remember your exponential. Exponential looks like that. This exponential passes the vertical line test, so it's a function. It also passes the horizontal line test, so its inverse is also a function. So we would call that one-to-one. So that is a little bit of a definition for what it means to be one-to-one and what it means to have an inverse that is also a function. So what we want to do right here is determine if it's one-to-one, not by looking at a graph, by doing it analytically. So this example, I have these happening right here. I want to find out, is this one-to-one? Does it pass the vertical line test and the horizontal line test? Now, if I want to do this by hand, use this definition right here, where it says, if f of c equals f of d, then c equals d. So let me show you what that means. I'm going to come in here and do f of c equals f of d. So plug c in to get 1 over c plus 2 equals plug d in to get 1 over d plus 2. And then basically I want to simplify this. So first thing I'm going to do, times by c plus 2 to get that out of the denominator, and times by d plus 2 to get that out of the denominator. So I have d plus 2 equals c plus 2. And now I can minus 2 to both sides, and I end up with d equals c. That was the final part to our 1.11 definition. So you plug in f of c and f of d, simplify it, and see if you end with c equals d. So right there we can say, yes, we know this is 1-to-1. Now, we could also graph this. This is 1 over x, parent function, but that plus 2 inside the fraction is just going to move the whole function left 2 using our transformations. So I'm going to take my 1 over x parent graph and move it left 2. So here's our 1 over x parent graph. Hopefully you're working on memorizing those parent graphs. Has those asymptotes. And we can see graphically, does it pass the vertical line test? Vertical lines? Yeah, only crosses the graph once. So check. Does it pass the horizontal line test? Let's see. Like this? Yeah, it does. Only passes the graph once. So horizontal line test? Check. So that is the other way we know, yes, it is 1-to-1. So let's end by looking at B. Now, I'm going to warn you right now, B is harder than anything you're going to see on a test. This question's kind of a weird question, and you need to know a lot of stuff about factoring and all that good stuff. So if this one's confusing to you, that's okay. Just work your way through it and then move on. For us, we're going to start with that analytically stuff. G of C equals F of, G of C equals G of D. We're going to plug C in to get C squared minus 2x plus, C squared minus 2C plus 4 equals D squared minus 2D plus 4. Plugging C in on this side, plug in D on that side. Now I'm going to simplify this. So since it is a quadratic, I'm going to start by bringing everything to one side. And you'll notice the 4's go away. So I've got C squared minus D squared. And then I got minus 2C plus 2D equals 0. Now, you might remember from secondary math 2 that this is a special case. C squared minus D squared is your difference of squares. So it's C minus D, C plus D. That's how you factor your difference of squares. And if I lost you there, that's okay. We'll talk about difference of squares a lot more later on in chapter 2. Then if I come right here, if I factor out a negative 2 from these, I get C minus D. Just factored a negative 2 out of those. Now, if you look at this one and this one, you'll see that they have something in common. This one has a C minus D, and this one has a C minus D. So you could factor that out. If I take a C minus D out of that one, I'm left with C plus D. And if I take a C minus D out of that one, I'm left with a minus 2. So when I look at what I've got here, I can solve this one to get C equals D. Or I could solve this one to get C equals negative D plus 2. So I can see right here, C doesn't always equal D. I have it here, but not here. So that would tell us that this is not one-to-one. And we know that by looking at our parent graphs. I know that this is some sort of x squared. I know that this x squared points up because this is positive. X squared passes my vertical line test, but it does not pass the horizontal line test. So there I can say vertical line test, yep. Horizontal line test, nope. And just be done with it. This is not a one-to-one function. So in the next video, we'll explore inverses a little bit more. See you then.